Okay, calculus, let's get this done. We're going to be looking at some trig functions with differentiation. And we're going to go through the classwork problems with that. So remember, the big idea with differentiation that we're talking about this whole time is slope. And let's start off with that idea. Well, first, when we talked about the definition of derivatives using slope and limits, we kind of talked about this function right here. This is really, x plus h minus x, like that. So it looks like the difference in the y values over the difference in the x values, and then you shrink those down to 0 over 0, and it becomes this instantaneous slope. So we're looking for that instantaneous slope, the slope at that instant. Well, let's talk about those slopes. So we're going to look at this graph down here. We're going to look at the slopes of this graph at these points here, kind of like the typical benchmarks, at 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's do that. And then we're going to look at those values and kind of compare them, see what we come up with. So the first thing, the slope right here, at 0, the slope, not the location, but the slope. So the measure of this incline here is about 45 degrees, and that slope then would be just a 1 over 1 kind of slope, 1 over 1. So we're going to say that that slope is right here at 1. The next location is at pi over 2. This slope is entirely flat. Well, that means that the slope here at pi over 2 is actually at 0. So we started at 1, now we're at 0. So we're kind of having this downward trend in slope. So we were at 1, but then we flatten out to 0. After that, the next one, we're looking at this slope here. And it's inverse, pretty much reciprocal of this other one, not reciprocal, but inverse, multiplicative inverse. In other words, it's not positive 1, but it's negative 1 right here. It's going down 1 over 1. Well, if that slope is at negative 1, then I'm going to mark a point down here at negative 1. So here's 3 slopes in a row. I start at positive 1, then I go to 0, and now I'm at negative 1. Similarly, I'm going to make my way back now. So at 3 pi over 2, again, we're flat right here. And then at 2 pi, we're back to that positive, so it's up here. Now, if I were to connect these dots that I just made, but do it in a curving manner similar to like a sine or trig type wave, I have a very similar wave here, but it's just slightly offset. So let's look at these values. At 0, my slope was 1, approximately. It's actually exactly 1, but it looks like it's 1. Pi over 2 was 0. Pi, it was at negative 1, then 0, then 1. And if I were to look at these values, this kind of red dotted line, that's actually very similar to a known trig function. What's the derivative? Kind of, if we connect the dots, what trig function does the derivative of this suggest? It suggests that the derivative, DDX of sine x, is cosine x. And that's very true. That's exactly what it is. So now let's look at the next one here. We're going to see another interesting relationship. Let's use purple for this one. Okay, so now we're starting out with a flat slope here at the beginning. So that means my slope this time is going to be 0. Then I immediately go into that downward trend, which would be down here at negative 1. Next, I flatten out again. So that's a slope of 0. And now I get back up to the incline. So this slope is going to be up here at 1. And then we flatten out one last time. So we were inclining, and now we're flat again. So I'm going to connect these dots with a similar kind of curve. Okay, and you would look at that and you're like, it looks like it's offset again. So would it be sine of x? I'm not sure. It's a little kind of unsure there. So at 0, we're 0. Pi over 2, negative 1. Pi is 0 again, and then we're back at positive 1 and 0. It looks like sine of x, except sine of x, if you look back here for a second, this black curve, it went up and then down. So at pi over 2, it was positive 1, and at 3 pi over 2, it was negative 1. This one goes down and then up. So if you see that here, we're going down. Whoops. Let's undo that. We're going down and then up. So that inverse kind of relationship there implies to us that it's sine of x, but it's flipped. So when it's flipped like that, it's not just sine of x. It needs a negative in there. So that means that the derivative of y cosine of x, so the derivative of cosine of x, it's not just sine of x, but negative sine of x. And in fact, that's true. Basically, that's what trigs are in a nutshell. Trig derivatives are. So the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. Now, all this other junk here kind of gives you the other basic formats of all the other trig derivatives. Why do we really only need to know the first two, though? Well, because every trig function is a combination of sine and cosine. It's really only sine and cosine. We just use other ones as shortcut abbreviations. But if you did need to memorize kind of like what are known as like the 6 trig functions, here they are. And they're in your notes. And you need to work with them, and we need to memorize them eventually. But for right now, for today, we're going to be consulting this table quite a bit. So let's start out with just a few. We're going to be following general rules just like we do all the time. You know, the constants, the chain rule, product rule, quotient rule, but let's go ahead and jump right into this. So this first one, I see a constant times sine of x. So when I do the derivative of y primed, or dy dx, that constant has that tag-along effect, for the constant just disappears, comes back. Then we have the derivative of sine of x, which in this case is cosine of x. Easy, super easy. Now this next one, slightly different. Notice that the 2 is not out front, but now it's inside. Because whenever you have a trig function, there's implied grouping going on. Whatever's sitting right next to it is grouped. So that means now we have a function within a function. The outside part is sine, and the inside part is 2x. So we have a chain rule then. We're going to take the derivative of the outer layer, which in this case, the candy shell, I guess you could say, is sine of x. So y prime is going to be cosine. Then we leave that inner layer alone the first time, so it's just 2x. Then we multiply by the derivative of that inside layer, which is 2. Now, to look at part C here, it's actually just a combination of these two things. So you see that we have the constant outside, so that's going to tag along, but then we have this inside layer thing. Now I'm going to cheat a little bit. I already know what the derivative of sine of 2x is. Why? Because I just did it. And then I also know that this constant here is just going to tag along. So that's going to be a 2. And then we're going to multiply it by the derivative that we just found. Cosine of 2x times 2. Now if I were to simplify this to like a multiple choice type level, it would probably say 4 cosine 2x, like that. Alright, let's look at this next one. Now before I even get started, just a little caveat. I know that we use this sine squared notation, but we need to realize that that actually means it's sine of x quantity, the whole thing, squared. So in other words, sine of x times sine of x. So there's a couple of ways you can treat this. You can do a product rule with sine of x times sine of x, or we can do a chain rule with sine of x on the inside and squared on the outside. So that inside layer that I underlined twice, the sine of x, and the outside layer is the 2. Let's go ahead and use chain rule. That means the derivative of the outside is going to be 2 times the inside to the first power. The derivative, or we leave the sine of x alone the first time. But then we're going to multiply by its derivative, which in this case is cosine of x. So we would have, written more simply, 2 sine of x cosine of x. Next, okay, now, layers upon layers. So first I'm going to rewrite this. I'm going to write it as y equals sine of 2x squared. So that's what it actually means. And then in looking at this, what I'm going to do is I'm going to identify the layers, make a plan for where I'm going to go. First, I see this 2 as the outermost layer. Next is going to be the sine, which will be the middle layer. And then this 2x, which is the inside layer. Now, if I put those three things together, let's start with that outside layer. Y prime, our derivative, is going to be the 2 on the outside, and then we're going to wind up raising to a first power. So we're going to leave the other two layers alone for this first one. Next, we're going to multiply by that middle layer. The middle layer is going to be cosine. That's the derivative of the middle layer. And again, we leave the next layer alone. Then we're going to multiply all of that by the inside layer derivative, which is 2. Now we stop because we've done all three layers. If I were to simplify this to like a multiple choice type answer, we'd see the 2 and the 2 would be a 4. And we'd have sine of 2x times cosine 2x. Not a whole lot of simplifying, but still worth considering. Let's go ahead and look at f. Very similar, but actually not quite as complicated, in my opinion, of course. So the first thing I want to do is I want to look at this as sine, and then I'm going to have something on the inside here. Instead of square root of x, I'll write it as a polynomial, x to the 1/2. So I got layers. Outside is sine, inside is x to the 1/2. Let's start with the outside layer. Y prime is going to be cosine of x to the 1/2 times, now the derivative of x to the 1/2, which in this case is 1/2 x to the negative 1/2. Now if I were to simplify this to a multiple choice type answer, I'd have cosine square root of x on top, because that's all to a positive power. But here, this 2 is in the bottom, in the denominator, and x to the negative 1/2 means that's also in the denominator, so it'd be square root of x in the bottom now. So that would be our next one. For this one, I really want you to see this juxtaposition of moving things around and how it has an effect on the derivative as far as what's inside and what's outside. For this next one, we're looking at a function that does have a square root in it, but now it's on the outside. So we have sine of x on the inside, but on the outside, the 1/2 power. So when I do the derivative y prime, I'm going to have 1/2, and then the power up on the top right here is going to change to negative 1/2. And then we leave the inside layer alone for the first round, but then we come back to it for its derivative. Sine of x derivative is cosine of x. So now that we have all that, we're going to have a little bit more simplification. We got some things going to a denominator, some things in square root. Let's sort them all out. So I'm going to have y prime equals, now when I know I have numerators and denominators, sometimes I just go ahead and write my dividing bar and see what's on top, what's on bottom. So I have a 2 on the bottom from this 1/2. I also have a square root of sine of x, because that's sine of x to the negative 1/2. Then on top, I'll have that cosine of x function left over. So there we go so far. We're probably going to pause it after this one just for a short intermission, just so you don't have to watch too long of a video, just to give you a break. And if not, you should be kind of breaking yourself in these videos anyways. Let's start with h here. Let's first rewrite, and then we'll make a plan. Y equals, we're going to have something to the 1/2 power, and we're going to have sine and of 2x on the inside. So again, it's really helpful if you identify the layers and then work through them one at a time. I see that I have this 1/2 on the outside as my first layer. Sine in the middle is my second layer. And then the most inner layer, the inside layer, is this 2x. So we got 1, 2, 3. So when I look at y prime, I'm going to start with the outside layer. That's going to be 1/2. Then I'm going to leave the inside alone this time. And the power is negative 1/2. So the inside is sine of 2x. Now I'm going to multiply that by the derivative of the second layer, which is cosine of 2x, leaving the inside alone this time. Then thirdly, the third layer that we multiply it here, is times 2. Okay, so let's look at this piece by piece, because it's good to practice our simplification exercises. So we have a dividing bar. We know we're going to have a 2 on bottom here. We're also going to have a 2 on top from that 2. Those are going to wind up reducing or simplifying to 1. This sine of 2x to the negative 1/2 is going to go to the bottom. It's negative 1/2 means a square root on the bottom. And on top we're going to have cosine 2x. So this 2 and this 2 make 1 over 1. There you go. That's what our multiple choice answer would look like. So let's go ahead and stop this video. We're going to do a part 2 just to kind of keep it rolling here with the slightly shorter videos, a little bit easier to follow along. Take a break.